Hello and welcome to Kaggle Basics Part 5. For this video we will only need a small brain. We do not need a large brain, so that is why I have the small brain modification on right now. For this video we are going to be implementing the new code, the old code actually, from the housing price prediction and implementing it on StarCraft 2 ranking prediction. So, let us begin to do that. And I'm just going to put this back to normal too. Okay, so let's go to Kaggle.com. And I already ran the code as well, so we'll just go through it super fast. If you go to code and then you go to your work, you'll notice some codes here. And you can literally take the entirety of the housing dataset code that we used before and implement it on a different dataset which has similar goals and things that you want to accomplish. Multivariate analysis and prediction of one component. For that case, it was housing price. For this case, it'll be StarCraft 2 rank. So let's go to this code, and I'll point one quick thing out. If you've ran a code and submitted it, then what you can do here is you can go to settings, and this is how you make a code public. Settings and visibility. If you want to make your code public, you can make it public, otherwise keep it private. This one I'll keep private. I'll go back. Well, I already have it open in this tab here. It's the StarCraft ranking prediction tab right here. Continue editing. Move this out of my way. And we can go through this step by step. A few quick things about StarCraft is that there are, I think, 7 different ranks from, well, let's go to this one, Kaggle, and go to datasets. Let's search StarCraft Skillcraft. This is the dataset that I was using. Pretty straightforward. Here's all the different variables that are in it: game ID, league index, age, hours per week. So basically all these variables for a specific player, actions per minute. And if you don't know that much about StarCraft, I don't want to go too much into the details of what all of this is, but actions per minute is basically just different clicks or maneuvers you're making every minute. A good player has, I don't know, 100 to 200 APM. I'll get into more of that. Complex units made, PACs, all of these different variables that have to do with StarCraft. There are only 6 codes. This isn't a very popular data set, but it is really cool, so it should be popular. Predicting player placement, and here's my code here, StarCraft ranking prediction. So let's go to that code and see what I did and how I just essentially just took that code from housing prices dataset and almost copy and pasted it directly into here. And there's some improvements we can make to this code, which I will write down as we do get to them, because I may do that in my spare time. But first, let's just go through it and see exactly what it is. So first we are just, let me zoom in a little. First we are just importing all of the libraries here. Now we're reading this Skillcraft CSV file. It was a little bit different than the last input file, you have to just figure out where it is here. Here's input, right? So there it is. Input skillcraft, skillcraft CSV. That's a StarCraft pun to anyone who knows StarCraft. And then we look at the data head here. League index, age 27, hours per week, 10, 3,000 total hours, 150 APM, selection by hotkeys. You have all the variables here. And what's their rank? League index is 5. So I think that it's going to go 1, 2, 3, 4, 5, 6, 7. And that's bronze, silver, gold, platinum. Is it platinum? Masters, let's see. Let's just make sure before we... Okay, bronze, silver, gold, platinum, diamond, master, grandmaster, and that's it. A grandmaster is as high as you can be. I rank as a platinum player, but that doesn't really matter. Let's keep going. Now we're going to drop some features. Which feature are we dropping here? We're dropping the ID column. Let's look at the ID column. It doesn't mean anything. 52, 55. It does, this column doesn't give anything. We can look back on this tab and make sure. Unique ID number for each game. So I don't know why that's there. I just dropped it from the data set. I don't know what it means. Maybe I'm missing something, but I think it's okay. You just drop that. Now we look at the next one here. Total hours. Oh, this is, I'm saying, let's predict the most valuable predictors for rank. And I would imagine that total hours would be a very good predictor. Hours per week, that's probably shouldn't be number 2, but that's what I wrote. Actions per minute. So this is where it gets tricky if you don't know StarCraft, but essentially different races are going to have a different APM, and right now a lot of people are going to say I'm making excuses for Protoss, but Protoss, you just have a lower APM when you play Protoss, because I am a Zerg and I play Protoss 2, and my APM is different on both of those, but my rank is the same. I'm platinum on both of those, but my APM for Protoss is like 80, 70 or 80, and then for Zerg it's like 150, because you just have to do more stuff. But so APM is a little bit race dependent, so that's one way they could improve this data set, is by showing what race the player is, which they don't do. And gap between PSEs. PSE is basically like how fast the player is shifting their attention to different parts of the map. And then 5, select by hotkeys. So now we can look at those, and if we look at these plots here, we can already see an outlier, so we can drop that. But in the meantime, I won't drop that. I'll leave it in, and I'll just look at a closer look at this. So total hours, we're not seeing a good relationship here. So immediately, this is a flaw in the data set. There's no way that a rank 7 is Grandmaster. So there's no way somebody played less than 1,000 hours and became a Grandmaster. That's maybe it's possible. I don't think it's possible, but if you look at the quantity of players that did that, you could clearly tell that obviously these are people that started a new account and they haven't logged their total hours onto that account. That can be the only explanation. So that means that total hours is not a good predictor, so I might even have to drop that from the dataset. What was going to be my best predictor actually might not be that good because it is not accurate. If the data is not accurate, it cannot be a good predictor. So we keep going. Here's APM. We do see a nice little shift. You do have some lower APMs at Grandmaster. I mean, look at that, 150, less than 150 APM as Grandmaster. That's crazy. But that just shows you that the game is a very complex game, very strategic game, and you can have a high rank with a low APM. But uh, APM is somewhat a predictor of league index. So we can keep going and look at different things. This one was hours per week. Not much we can say from that plot. This plot is number of PACs. We see a clear increase the higher the number of PACs. We're not seeing the best relationships, the best linear scatter plots, but they're pretty good. Another thing I could have used here, that's going to be my first improvement, is these scatter plots aren't the best plot. They should be box and whisker plots. So that's one improvement I will make to this. Is that if these are box and whisker plots, that's going to be way better, and you can get a better understanding and feel for the data set. So we continue on. Not much to predict here. Selection by hotkeys. Again, you do see an increase there. I mean, it looks like some of the masters are using a ton of hotkeys. Are utilizing the hotkeys. Selection by hotkeys doesn't mean... It means, yeah, what's up, Ethan? Okay, I'll be down in a minute. Alright, so selection by hotkeys means that's how many times you select a unit using the hotkey, not creating it into a hotkey. At least I'm pretty sure. Let's double check that. Number of units or building selections made by using the hotkey. Assign hotkeys is how many times you assign a unit to a hotkey. So that's all well and good. Right now we're just looking at the data. And now we can start looking at distributions, just like we did on the housing price. I'm just taking that code and using it here and thinking about improvements I can make to the code. But in the first run through, it should be fine. It should still predict what we want it to predict. I mean, it's not like you have to write an entire new code for this. So we can see here, it's a somewhat normal distribution. The probability plot's okay too. So I say let's just leave it. It's fine. Maybe it would have been better to do a log transformation. I don't really know. I didn't try that. I did try a few things though to get a good prediction, and I'll explain those as we go. Now we look at the correlation map. So I think I say, yeah, it's like a cheat move. I didn't need to do all this. I probably should have just done the correlation map first to see what's the best predictor of league index. And which one is it? It looks like this is a good one. APM. And this is a good one. Number of PACs. And this is a good one. Assigned to hotkeys. This would be a bad one, right? Actions in PAC. This would be a bad one. Gap between PACs. So you can kind of figure out what's going to be your best predictors of league index or StarCraft rank. So what are we dropping now? Let's go ahead and drop league index because that's what we're predicting. We don't need that in our tensor. I guess it's either a tensor or an array. So let's drop that right out of there. And the data size before dropping it is this. So it's actually just a matrix, right? Two-dimensional matrix. And then we go from 19 columns here to 18 because we dropped it out. And we initially had 20, but we got rid of game ID. And then we are now getting rid of league index. So now we're at 18 columns, but still the same amount of players, 3,338 players. Now we check for our missing data. Good thing about this data set, it's not like the Ames Iowa data set. There is no missing data. Continuing down, let's do a distribution plot. Here we go. Actions per minute. Not the best distribution. It's got a slight skew to it. Okay. So it looks like we're probably going to be doing some type of transformation. If you remember, there were two options that we really looked at so far, which is log transformation and then the box cox transformation. Either one's okay. Normally, when you're for the first look at a data set, I would say start with log, but there are different transformations you apply based on what this is. So I think we went over that in a previous video, based on what your distribution looks like. For this one, let's go with a log transformation. So now we have a bit of skew. Let's look at the skew in all of these. Looks like total hours has the most skew. No surprise there. Even though that doesn't have to do with its ability to predict league index, that's just skew, right? So I guess it's a little bit surprising that it's so heavily skewed. Minimap attacks, all of these. Okay, so let's go ahead and blindly apply a log transformation. And I did also try the box cox on this one. I think the log outperformed it. The best way you can do it is look at each individual variable, each one, and then apply a specific transformation to that. But we're not interested in creating the best prediction in the world here. I'm just trying to give you a brief overview. So instead of doing that, let's just apply a log transformation to all of these and see how well that does. Here's the skew initially. We apply a log transformation to all of them which have a skew above 0.75, which is assigned to hotkeys and up. Boom, we apply it. Now we look at actions per minute again. Look at that. Beautiful. It worked. We just waved a magic wand and voila. Actions per minute is now a normal distribution. Keep going through here. Look at the skew. They're all down. Not super far down for minimap attacks, but it is what it is. A lot of them look much better. Some are negatively skewed now. Actions per minute went all the way down to negative skew. But this is all good. If it's below 0.75, that's pretty good. Maybe we could further improve upon that. That'll be my next improvement. Look into the variables that were not fixed from applying a log transformation. So we would have to revisit these and figure out what would be a better data transformation to apply, and apply that. And the closer that gets to a normal distribution, the better it is for our predictive capabilities. But who cares about that? We're just running through this thing real quick. Now we split it up into a training and a testing. So this is important. This isn't like a competition. This is just some nice person who made a good data set, and they didn't divvy it up into test and train. So we're going to do that ourselves. Sometimes you have to do that. We're gonna do an 80-20 split on this. So we're only going to train on 80% of the data set and test on 20%. Could be better if you randomly split this up, but I don't think it matters. So I just took the first 80% and put it in one, and the final 20% and put it in another. Here's the shapes of those. Okay, good. Now let's implement the models and see how well these models can perform on this data set. So we haven't done anything new. We're just taking what we already had here and applying it to this entirely different data set, an entirely different thing that we want to predict. So we're importing elastic net, lasso, Bayesian ridge. And remember, we went over these, and I said you can look into them further and learn how to utilize them and improve on them, but you don't have to know exactly all the mathematics behind all of these different models. Sometimes you could just apply them and see how well they do, and see which variables are best tuned to improve the predictive capability. So here we go. Let's import all of these And when we import them here, this is when we are bringing in stuff that we can, these are called hyperparameters. We can adjust these hyperparameters to get better predictive capability. You do have to learn a little bit about the model to, kind of know what you're doing, not just change things blindly, but, you don't have to know everything. So I didn't optimize these either. So it does take a little bit of computational time to run each model and check each hyperparameter. Like if I change this to 0.01 or 0.05, what effect does that have on the predictive capability of the gradient boosting regressor method? You have to run it 5 times to figure that out. You can get a path but you don't have to. So anyway, let's just test all these models out. Look how good our accuracy is just from taking that one and plugging it right in here. 0.94. That's a really good error. What are we scoring this based off of? Negative mean squared error. So that's a good error to have. That's not 94% accuracy, by the way. That's a 0.94%. Not percent. It's just the error. And different errors you can get. Let's just pull that up while we're in this video, because this makes a big difference. I think let me keep going and I'll pull it up in a minute. So all of these are about 0.93, 0.94. Now we try these models, the XGB regressor, LGBM regressor. This one gets 0.94. This one gets 0.90. So that one did really good. And then I'm going to average the models just like we did in the other video. So we're just taking the average of all these models and seeing how well it does. And look, it improved it right away to 0.91. And let me pull up mean squared error. Mean squared error. I think that there could be a better way to Google that too. Metrics. Okay, so from sklearn.metrics, import mean squared error, accuracy score, mean absolute error. So this is what we want to Google. And we want to see all of the different metrics that we can utilize. And we are using regression. So if you look over here, we're going to click on regression metrics. And this is it. This is all the math for all of the error that is found. And look how easy it is to look here. This is the true 3271. This one's 9271. The max error is 6. That's that one, 3 to 9. So this is how you look and figure out what metric am I using? Do I have a good score or not? How many am I predicting right? Mean absolute error. Is that what I used? I think I did, right? In the end. RMSLE, so mean squared error. Okay, so I used mean squared error. So that would lower it a little bit. The absolute error would be more than the squared error. So here's the mean absolute error. Here's the mean squared error. Oh, so they square it. So actually that would be higher, I guess. I'm not sure. Absolute error would be higher. Here's a 0.85. Same situation here. 0.70. So, you can look at the math of all of these and figure out, like, this is how far away it is from the actual. actual minus predicted squared. That's it. That's all they're doing. I mean, it's a big math equation, but that's it. That's all they're doing. And then logarithmic. Okay, so they're going to take the log somehow, whatever. Mean absolute percentage error. So then we can actually get a percentage error, but that doesn't mean that you're 95% accurate. The terminology kind of matters here. But the main point is that we evaluated these using a mean squared error, and we were able to get a mean squared error of 0.73 with just taking this code that we already used and applying it to StarCraft 2 rank prediction. One more thing I want to say. The average model, obviously, it did better. Once you average all of these models together, just like we did in a previous video, it did better. And finally, how did I get from 0.76 to 0.73? I rounded it. So I took the entire prediction, stacked pred rounded, and I rounded it. That's a very simple mathematical operation. The reason I did that was because what we want to predict is an integer. We want to predict, is it a 1, a 2, 3, all the way to 7. So if we round that out, like say you predict it to a 6.85, like we're predicting to a decimal, that doesn't necessarily make sense. I mean, it actually could make sense because they could break this rank apart into a continuous variable. It kind of does work that way almost. Like you don't just bump up one day from gold to platinum. You have to go through a certain amount of points or however they do it. And so it could be broken up into a decimal format. But it's fine like this. We'll just round it. And so if we're predicting it to be a 5.58 and the rank was actually 6, so then we get a closer prediction on that. So that's just one little thing. And in some cases, the rounding might work against you, right? If you round down. But in most cases, it'll probably help. And it looks like it did just by rounding it. 0.76. Then we dropped it to, this is without rounding, and this is with rounding. And we're looking at the mean absolute error of that. We're printing it out. Pretty close, and a pretty good job, too. I mean, that's impressive. And also, I should mention that this is using the models on the testing data set as well. So that's pretty impressive. That's not the training. So we trained with the training data set. That's what these ones did. All of these models. We trained them. We combined them. And then we applied that model that we trained using the training data set on the testing data set. It never saw the test data. So that's very impressive to get that high of a score with just doing a tiny bit of work. So that's all I wanted to show you today. The main thing is now we could improve this code. I did make this code public, so I did that by going to the thing I showed you in the beginning, settings, and then making it public. One thing we can improve is the box and whisker plots here. We could do a better job of transforming the variables so that they are more normally distributed. And then a third thing I think we could do is tune the hyperparameters of the models, which are here. These are the hyperparameters. So that's computationally intensive in some cases. It's not super computationally intensive in this case, but still does take some time. So improve hyperparameters. And the last thing is, I think that there was one more option. If we go to this housing dataset code, he does something at the end in this code that I didn't do. I can't remember what it's called. It's not averaging. Adding a meta model. So we could add in this meta model. I could literally copy and paste this. But I'm not super keen on what this is, so I didn't do it. But I certainly could, because he does one thing that I didn't fully understand here, where he takes this and multiplies it by 0.7 and this by 0.15 and this by 0.15. So it's kind of like using three different models there. But it worked. It got him a really good score, prediction score. So that's fine. Uh, so we could add in a meta model. That's the fourth improvement we could make to this code. But the main things, I mean, just by tuning the hyperparameters and doing better transformations on the variables, that's the main stuff that we want to be doing, not getting into the super advanced modeling techniques. Eventually you want to do that, but you can get a lot of value just from tuning hyperparameters. Okay, so that's it, and thank you for watching.